Hello? I guess it's time. Well, welcome. I don't suppose Adam came. Is Adam here? I told him last night on the bus to the speaker dinner about my favorite Swedish candy from Cloetta. That I've been to Sweden a lot, and I always buy the candy to take home to my children, or I did when they were smaller, and I told him about their favorite, and he didn't believe that there was a candy with this name that's called Plop. And so I found it, that one of the booths right across is giving it away, so I got a couple, and I want to give them to Adam to show him. Yes, it's really a candy. So, speaking of sweet things, we get to talk about something really, really sweet, and I didn't plan that segue. That just popped into my head right now, but I really do think this new feature is very, very exciting. I have just a plain old name for it, and this is the only place in the official slides that I will say that I have written the word Hekaton. If you see a Microsoft presenter giving a similar talk, they don't say Hekaton at all. That was the code name, and now they're calling it on the first line there, in-memory OLTP. How long does that take to say every time? How long does it take to type every time? So I will tell you, when I talk, I still say Hekaton, but I had to make sure that in the written slides, I didn't say Hekaton, except on this front one where I put it in the quotes. It's so much easier to say the new Hekaton system than the in-memory OLTP. It's so easy to say Hekaton table than memory optimized table. So when I talk, I probably will still say Hekaton. And Brent last night gave me a better title for the presentation. I didn't get to change the slides to say it, but the title really should have been, What the Hekaton? You can laugh. I will tell Brent that you laughed a little and not very much. Brent's here! Brent, hi! Thank you for that title. So you heard how little they laughed, so it really wasn't that funny after all. Okay. So, a little bit of background here. The most important thing is I've been working with SQL Server for a long, long time, just had the 26-year anniversary, and I still really love it. I keep thinking next version is going to be my last version, and then Microsoft comes out with something really exciting, like Hekaton. And I decide, oh, I'll stick around for a little longer. I got to learn about this new technology, and then maybe I'll retire after that, but who knows what they're going to come up with in the next version. 2012, though, it's almost old news, right? I did write a book for 2012. It was done over a year ago, except it sat in the publisher's files, and nobody at the publisher did anything with it until just very recently. Finally, just this last summer, they started to move on it, and just this morning, so you guys are the first to hear, I got an official email that said, we have everything we need now, we need nothing more, and we're sending it to the actual publisher. So there really will be a book, but just in time for yet another version. But at least my co-authors, I felt particularly bad for them that they had worked on the book and never got to see it printed, but it will be printed. My 2012 internals book will be out while it is still 2013, as it says on the slide. And then some of you might be aware I've written a white paper on Hekaton, and I will be continuing to update that. In fact, I might even turn it into a book. I've been talking to the people at Redgate about turning the white paper, maybe doubling the length and turning it into a book. So any questions that you have that I'm not able to answer here, or that you're not able to ask here, I have a special alias for questions and specific areas of interest that you would like to see addressed in the book. So if you want to make a note of that address, it's HKWP, which is for Hekaton White Paper at SQLServerInternals.com, which is my domain. Feel free to send suggestions and questions. I will not be responding and answering all the questions directly, but I will use them as guidelines for how to expand the white paper into a whole book. So What is this new in-memory OLTP? Some of you might have heard some rumors. I thought, I guess I hang around in different circles than other people, but I just assumed everybody had heard about this. And then just yesterday, during the pre-conference sessions at the breaks there, talking to people, several of the delegates in my session yesterday said, "So what is this thing you're talking about tomorrow?" And I gave them a few quick sentences, and they said they had never heard about it at all. So that was very surprising to me, because that's been my whole life for like the last 6 months. But we all do different things. We have different jobs, and maybe you've heard something about it. Maybe you've heard not very much. Maybe you've heard a whole lot, but you just want to hear more. So I'll tell you more. What the basic things to keep in mind. This slide will just be the overview of the things that I will be covering throughout the session today, that this is an in-memory technology. The tables and indexes have completely redesigned structures to take advantage of being in memory. In fact, we really don't even have tables anymore. Logically, you can think of tables. We have to have tables to be a relational database, but they're only logical. There is no physical table. There are no physical table pages. The data exists only as rows. And because there are no pages that need to be maintained, SQL Server doesn't have to keep track of specific locations on disk where each page belongs. When it writes your rows out to disk, it actually uses a stream technology to just write everything out sequentially, and it makes the writing much more efficient as well. One of the main changes with the new in-memory OLTP that we won't really be addressing, because this is more for DBAs today, is that there is a new flavor of stored procedure that is actually completely compiled, natively compiled into a DLL and stored as part of the SQL Server to process the operations that you're doing. That will not be covered in much more detail, but it's something a DBA needs to be aware that these DLLs will take memory. And when we talk about memory planning, you'll need to, at least in your mind, think, oh, plus whatever memory we need to hold these DLLs. And I think the biggest excitement in the new in-memory OLTP is the fact that these new data structures designed to hold your tables and indexes are completely latch and lock free. One of the ways that happens, we're not going to be able to dive into all the details just in an hour, but one of the ways that they are completely, where no locking is required, is because no updates ever happen. SQL Server doesn't take a row, and when you update it, it doesn't just change the bytes in the row. It creates a brand new row. Change inserts, of course, create new rows. Deletes just mark the rows as deleted, and they're cleaned up later. And updates are always delete the old row, insert something brand new. So this is what gives us multi-versioning, and it's built into the table structures to deal with the multiple versions of the same data very, very efficiently. But what that means, here's a little aside, if there's no latching and locking, then my most recent book, SQL Server Concurrency from Redgate, will just be totally meaningless. Everything that I wrote about concurrency here will no longer mean anything if you're using the memory optimized tables, so I might as well just get rid of all these books. I've got 2 here that I need to get rid of. Redgate across the aisle has 9 more. After this session, you can see if you're one of the first 9 to go get them, or if I get some really good questions, I might give one of these 2 away. But everything is going to change. And what Microsoft claims is that the biggest boon, their biggest marketing message from the Hekaton storage, is that this capability is fully integrated into SQL Server. You install SQL Server 2014 and you get the ability to create tables in memory. It's not a separate component, it's not a separate checkbox during install that you say, I want this capability. It's part of the core SQL Server engine. Let me just make a strong point now, though, That doesn't mean every single one of your tables should be created as an in-memory table. The planning and design that you're going to have to do is not going to be any different from the planning and design to design structures for disk-based storage, which is usually the word used to mean the non-Hekaton tables. We have disk-based tables and we have in-memory or Hekaton tables. As part of your design, you would now consider, will this table be more efficient? Will this table be able to take advantage of being stored in memory completely? The tools that we've always used for managing our data will still be able to be used for managing our in-memory tables. Management Studio will show us the in-memory tables along with the rest of our tables. We will still have SMO capabilities, but there's a whole new suite of dynamic management views just for showing the in-memory objects. And those of you that have worked with the DMVs a lot know that every family of DMVs has that little prefix that indicates what area of the product. So it's sys.dm underscore, and then the next component is what part of the product. Well, all the Hekaton tables have a prefix there of XTP. And I'd been working with them for a while, working on the first iteration of the white paper, and I finally got around to asking one of the engineers, well, what does XTP stand for? And you guys get to find out now. It stands for Extreme Transaction Processing. XTP, if you see that in a DMV name, it's one specifically added to work with your memory optimized tables. So there's a whole lot. I could talk about memory optimized tables, but what I'm going to focus on are the topics here. I'm going to look at the actual structures used for storing your rows and the indexes that connect those rows. I'll talk a bit about what you need to be aware of as a DBA as far as managing memory, and then how memory space is managed with the garbage collection routine, because you don't want deleted rows to take up all your space in memory. So how does garbage collection of unneeded rows take place? How, if the data is totally in memory, what happens when SQL servers shut down? How is the data actually persisted on disk? And one of my colleagues just this weekend said when he was reading the white paper, one thing he found not completely clear, I think he was just reading it too fast, but maybe I'll make it clear on the next iteration. He was like looking for what replaced the MDF file. Where's the actual data? Where is it stored? And I actually do say that in the white paper, but I will be telling you, and there is no MDF file anymore. There is no disk location that is the representation of all your data in memory. I will show you how the persistence is managed. If your SQL Server shuts down, you are able to recover all your data that you've wanted to be persisted will still be there. There's no danger there, but it's managed completely differently with the relationship between what's in memory and what's on disk. And then we'll talk about what gets logged when you manage your in-memory data, and then how the recovery works. So, as I mentioned, there are no pages, there are just rows. Your tables are made up of rows and rows and rows, and the structure of the rows is designed to be optimized, to be beneficial for in-memory access and not disk-based access. There's only one copy of every row. Columns from the rows are not copied into the indexes, not like with our regular clustered and non-clustered where we can have lots of the key values duplicated in an index. The indexes don't duplicate anything that's in the index rows, they just have pointers to rows. And a key point here is that without an index, you don't have a table. Every table has to have at least one index, because that's what combines the rows together into a single structure. Without an index, you just have these free-floating rows, and SQL Server wouldn't know which rows were part of the same table. It's the indexes that connect the rows together and say that they are part of the same table. The structure we'll be looking at on the next slide shows what the rows look like, but one thing I'll mention now is there is an upper limit to a very small upper limit to the number of indexes you can have, which in some ways is a good thing. You never want too many indexes. It's a much smaller upper limit than in your disk-based storage, and I'll mention that specific number when we look at the actual structure of the rows. So the indexes themselves are a bunch of pointers. We've got slides to show you how they're organized. There are two types of indexes for your in-memory tables. I'm going to focus a little more on the second kind because it's new in CTP2. There have been several presentations at the past conferences at TechEd on very similar content of what I'm delivering now. In fact, the slides here were based on one of the TechEd presentations. Some of the animations that I will be showing you were actually taken from a TechEd presentation. But at that point, CTP1 was all that was available, and we only had one kind of index. So the second kind, I don't think has really been presented much yet, so I'm going to spend a little more time on that. But the two flavors of indexes we have are hash indexes, which are optimized for equality searching, looking for one specific value. And we have a whole new structure for B trees. They're actually called BW trees. We'll see that on a subsequent slide, and that's what's used for range searching and for ordered scans. I mentioned that without indexes you don't have a table. Another point to keep in mind is that the indexes are never written to disk. The indexes only exist when the rows are in memory, and the only thing that's written to disk is the contents of the rows themselves. When you have to do a recovery, the indexes are rebuilt as the rows are loaded in. So this is sort of what a row looks like. Every row has a row header, and then it has the actual contents, the payload, which I'm not focusing on here. But the header, I'm going to tell you about a few of the values that show up in the row header. The system maintains a timestamp to keep track of operations performed on memory-optimized data. Every transaction, as it commits, gets a timestamp, and that becomes the timestamp for that row, and that becomes the system timestamp until the next transaction takes place, and then the system timestamp increases. Every row that's inserted has a begin timestamp, which is the time that row was inserted. It's the time that the row is actually valid from, and then it has the time that that row is valid to, the transaction that actually removed that row. So every row has a time, begin and an end that other transactions, excuse me, when they see this row, will know whether or not the row is valid. If another transaction starts after this one was deleted, it will, after the end timestamp of this row has passed, it will know that this row is not available. That's how the multiple versions can be managed. One of the limitations because of this structure is there are no large object data types allowed in memory optimized tables. We can only have almost all the regular data types are allowed as long as the row size doesn't exceed 8060 bytes, so we can't have the large object types like varchar max, var binary max, and row overflow is not supported. So if we have variable length columns, the total of all of them cannot add up to more than the 8060 bytes allowed in a row. Most of the restrictions on the tables themselves are not in the data types, but in the other schema properties of the table, things like constraints. There's a limit in the constraints that are supported. For example, foreign keys in the current version are not supported as part of the table definition. So again, it's the indexes that combine the rows together and make a table. The two kinds of indexes are listed here. We have hash indexes. In your table definition, you define the index as a non-clustered hash. Another point implied from this, what I just said, is you can't add indexes after table creation. all indexes are defined at the time you create the table. And you can define a non-clustered index, and you can define a non-clustered hash index, and the other kind is just written as plain old non-clustered. And I've complained about this actually. I said, this is going to be really confusing for people. If you call them both non-clustered, and one you have to add the hash and the other you don't. The one without the hash we call a range index, which is why I have the quotes around it, but range is not part of the DLL, the DDL is not part of your table definition anywhere. You don't say the word range. We talk about them as range indexes, but when defining them in our table definition, we just say non-clustered without the word hash. When we create a hash index, or when we define a hash index, we set a number of buckets in the hash table. And the more you've worked with hashing, the more this will make sense. This is not a place where I'm going to explain what hashing is all about, but hashing keeps track of data through a hash table with a number of buckets, and that is predefined. I'll tell you a little bit about how you might decide on a number of buckets. And that number never changes for the life of the table, no matter how many or how few rows you put in that table. Range indexes are stored as this new BW tree structure. I'll show you what that looks like in just a minute. So this is one slide illustrating a hash index. There was a presentation at Tech Ed on Hekaton for developers that went into a lot more detail on how this index was managed. But because our time is limited, all I'm going to show you is the final slide here, just to see a little bit about how the rows are connected together. This picture shows two hash indexes, an index on name and an index on city. And what that means is all rows with the same value for name will be pointed to from the same hash bucket. One pointer points to the first, and then the first one points to the second, and the second points to the third. Well, there are no duplicates for name here, so we've got three different pointers from the hash table for name pointing to the three different rows, Jane and John and Susan. None of them are linked to from the same bucket. The second hash index on the right is on city, and I do have some duplication there. So the hash table points to the row for Prague, the first row for Prague, and then you can see the pointer here with the Jane in Prague points to the row for John in Prague. And all the Prague rows would be linked together. One pointer from the hash table, and then all the Prague rows linked together. That's one way SQL Server could get all the rows in this table. And then another city is Bogota, and there are no duplicates there. So it's the hash pointer from the hash bucket points to the single row. And you can see in the rows the start and end timestamp. The first row, Jane in Prague, is valid from timestamp 50 and has not yet been deleted. So the end timestamp showing infinity basically means it's still there. It has not been deleted, and any transaction that starts after 50 will be able to see this row. The second row, any transaction that starts after 100 will be able to see this row. The third row was inserted at time 150, but deleted at time, was inserted at 90, deleted at time 150, so any transaction that starts after 150 will not be able to see that row. It is no longer there. I want to tell you a little bit more about range indexes, because this is what was new. Anybody who's just started to work with CTP2 or has only seen information based on the first CTP would not have had range indexes available. So range indexes don't have a fixed size like the number of hash buckets. They actually start out with 0 space required, and as you add more rows, the amount of space grows, and as rows are removed from the table, the size of the index can actually grow and shrink as you add and delete rows over time. One difference between the memory optimized range indexes and a regular B-tree index is that the the sequence of rows is unidirectional. We have pointers to the next values. We don't have any pointers to the previous values. If you want to do a descending sort, for example, on a column with a range index, you can if you've created the index as a descending index, but then you couldn't do an ascending search on it. So if you really want to do both ascending and descending, you have to actually use 2 of your limited number of indexes. And I think, now that I say that I forgot to tell you that. I meant to mention it on this page here. I mentioned the begin and the end timestamp, but then the statement within each transaction is also kept track of. Which statement within a particular transaction inserted this row is one of the values in the header. And then there's a set of 2-byte pointers, which are the index pointers. Or there's actually, there's a set of 2-byte pointers, and at most there are 8 of them. There's 2 bytes that say how many pointers are in this row, and then up to 8 of them are possible. 8 is the upper limit of indexes in the current design that we can have on a memory optimized table. So just like the rows themselves, everything in a range index is also completely lock-free. And it's based on this new B-tree structure that we will see shortly. There are similarities between the range index and the hash index in that if we actually have duplicate key values, they are linked together. Those pointers that are available in the data rows themselves will link duplicate values together. But how does SQL Server find the chain of one particular value? It doesn't use the hash table. It doesn't use the hash function. It actually uses a sorted sequence, very similar to our normal B-tree indexes. So the pages, the index pages, contain a set of key values. This is the only place you have any duplication between the data rows and the index rows is in the index pages. There are the index key values in sorted sequence, and the pointers to the page at the level below contain a high watermark showing what the largest value on that page can be. We'll see that when we've got a couple of animations over the next several slides. Just like the data rows themselves are never updated. Every time you update your data, you get new data rows for those values. The same is true for the pages in the BW tree indexes. That's the biggest difference between the BW trees and the normal B trees, is that you never update the pages. Every time a page needs to be changed, a whole new page is created. With the exception of leaf levels, those are not changed immediately. Those keep track of the changes in a set of delta values, and once you get enough delta values, then the page will be recreated. And this will be a little bit clearer in the animation that we're about to look at. Actually, I have a lot of pages on this. Probably shouldn't have had quite so many, but we will see it very shortly. And the trees are automatically maintained as you get a lot of deltas. You need to collapse them all into a new page. If you start doing inserts, pages may have to split. If you start doing deletes, adjacent pages may be needed, may have to be merged together. And so I'll show you all 3 of these operations, not in a whole lot of detail, but enough that you'll hopefully get at least some flavor of how this is different than the older B-tree indexes. So we have a mapping table. It's not the same as a hash table. The mapping table is a list of logical page numbers. Every page in an index has a page number, but where that actually exists in memory is kept track of in the mapping table. So in this, I'm just showing a little picture of pages 0 through 15, and each of those logical page numbers in this mapping table then has the actual memory address of where that page is. So this is a BW tree, and page 0 is the root. Where is that actually in memory? Well, the value in location 0 here says where that page is in memory. So here's the root. The root points to 3 pages, one that has an upper limit of the value 10, another value that has an upper limit of 20, and another that has an upper limit of 28 at this point. And then that's the second level of the index. At the second level, each index page, again, has pointers to pages at the level below, but I'm not showing you everything because the slide would get way too crowded. Down at this leaf level, this is the leaf level of the index. And oh, I know, I told you a few minutes ago that I argued with the people at Microsoft about just having the word non-clustered to define a range index because I thought it would be confusing. There's something here that I argued about and I actually won. That they were calling, in the index, they were talking about leaf level pages, and then all the pages above the leaf, they were calling the index pages. And wait a minute, index includes the leaf level pages. This is going to be very, very confusing for people that have actually worked with other index structures before to think of the index pages as not including the leaf level. And all of the internal communication that I saw when I was working on the white paper and people would write to me, that every time they would say index page, I would have to say, now does this include the root or not? And I finally talked to one of the program managers about this, and he said they are changing it. So they're now, all of the pages are index pages, and we have leaf pages, and we have internal pages. That's the terminology that they're using now. So I felt very, very vindicated about that. Okay, that's a little bit clearer now. So it's our leaf level pages that have every single one of the key values. 1, 2, 4, 6, 7, 8. I know you probably can't see that fine print up there. And I do have a zoomer, but I forgot to turn it on since we were starting so close to the actual start time. Let me see if I can actually get my zoomer. Do I have it there? I should have put it right in my desktop, but I didn't. I'm going to get the zoomer on. It's under Utilities. All right, does that do it? There we go. Okay, when I need to zoom, I'll be able to zoom now. So the leaf level on the leftmost page has the 1, 2, and 4 as existing key values. If there's duplicates, here's where we have the chains. So the value 1, there are actually 2 rows that have a 1, and here is where they're linked together. The 2, there's just 1 row for 2, and I'm not showing you the 4, and then the 6, 7, and 8 because the slide's getting too full already. So the upper levels, or the leaf and the upper levels, the index pages are what allow SQL Server to get to the rows. It doesn't use hashing, it uses an ordered search. And this is what allows a BW tree to be used if you have a range search or need to get the data in a particular order. But once we have duplicates, that's when we have the chaining, just like we do for hash indexes. So a couple of additional facts. Index page size, another difference between B trees and BW trees is that the page size is variable. Page size can be up to 8K, but it might be smaller than 8K. And let's see if I can actually, nope, it won't do the animation in the zoom. I think most of these points I mentioned already. Within the index, we have logical pointers. The physical pointers are only available through the mapping table. We're only linking pages in one direction. If we want to do both ascending and descending sorts, we have to have 2 different indexes for that. No updates on rows or on index pages are done in place. And there's not a specific concept of a covering index. The only thing that's ever stored in the index pages is the key. So now quickly, I want to just show you how the indexes are maintained without actually doing updates of the index pages. The three main index maintenance operations are consolidation of changes, consolidation of all the deltas, and then the split and the merge. So I'm going to step through these relatively quickly here. So there's our page mapping table on the lower left, pointing to an index leaf page showing a value of 1. If a value of 2 is then added to the table, 2 needs to go on that same page, but SQL Server is not going to take this existing page here and put a 2 on it. That would be an update of the page itself. The page would be changed. No, it's not going to do that. Instead, it creates a delta page and then updates the memory pointer that whenever we want to go to this page, we first go to the delta pointer that says, oh, keep in mind that while you're looking at this page, there's also a row with 2 on it. And then we get to the page and also see the 1. If another row is added that needs to go on that page, another delta record can be added. And every time a new delta record is added, the pointer, the physical address in the mapping table is updated to point to the most recent. And this is a ... in between the 17 and the 2, indicating that we've got a lot of deltas here now. The limit is 16. 16 deltas for a single page. As soon as you get the 17th delta, actually, no, that's the 16th delta because one row is already on the page. As soon as you get 16, that's the limit. SQL Server says, okay, I give up. You really want this page to be different, so we're going to give you a whole new page. As soon as you've got 16 changes to a page, it rebuilds the whole page, and gets rid of the whole old page. And the subsequent slides indicate original pages with a little bit of a white background. The previous page was white in the background, and then the colored background here indicates that this is a whole new page that has all the rows, all the values from 1 to 17 on it. No updates of the pages themselves. And then a split. We have page splits in our B tree indexes, but that actually updates existing pages, removes half the rows from it, takes another existing page and puts rows into it. For split on a BW tree page, in the picture here, we've got at the internal level, a 5, an 8, and a 10. The page with the upper limit of 5 is full. Notice that there really isn't even a 5. That doesn't matter for the B-tree indexes. It doesn't store the actual data values in the internal pages. It just stores what the maximum possible value on that page could be. The maximal possible value would be 5, even though I don't have a 5. But now I'm going to add a 5. I'm going to add a 5 to this page. And there's no room on the page for the 5. So what happens is 2 whole new pages are created. The green page and the blue page are created, and the rows are split between those whole new pages. And then the older leaf page is removed so that the green page points to the blue page, and then a whole new internal page is built. That's the one with the yellow background. And then the new yellow page has its pointers updated to point to the new leaf level pages. So everything is done on new data, and then the pointers are adjusted to include those new pages in the index structure. And I know this is fast and furious here. Well, not so furious, but I'm not stopping for a lot of details. I just want you to have a general feel for these operations here. And then we have a merge, but be careful because the Hekaton technology actually uses merge for 2 different purposes. We have merging of pages in a BW tree index. We also have merging of files on disk, which we will see very shortly. So a merge operation, if we end up deleting too many rows, in this picture here, I've got 3 rows on one page, 2 rows on the next page. I'm going to delete one of the rows on the second page, which is what this indicates here. I'm going to delete the 10. SQL Server puts something called a merge delta and an indication that the 10 is being deleted. Even at the index, well, the delete of the 10 is the delta record, and then a special record saying we're doing a delete of that value. And then it will create a whole new page for the upper level that removes the upper limit to the first page, and then a new page at the lower level, which has the contents of the 2 leaf pages combined together. So we had 2 pages, 5, 6, 7, 9, and 10, and we combined them into one new page and adjusted the pointers. 5, 6, 7, 9 all fit on a single row here. So point lookups, looking for a single row, can be done either with the hash indexes or with the BW trees. Range scans only can be done efficiently using the range indexes, searching the index for the starting point, and then anytime we've got duplicates, we follow the pointers through the chain of duplicates. There are some limitations in your table structures. I suggested this a little while ago. The slide here lists what some of those limitations are. I'm not going to step through these in detail here. They're all documented. There's some really nice documentation, and it's being improved all the time. Most important things here, I think I mentioned already. Constraints are limited, and you can't change an existing index. You can't add or remove any indexes or make any changes once the table's been created. You have a question?
On the subject of the identities, would you generate them in the application and feed them in, or would you use something like a sequence?
As far as what you would do to get around these limitations here, this is what you're asking. You know, at this point, I haven't actually started working on any kind of best practices. I was focusing on the actual storage. There is a document available online from Microsoft called the Hekaton Cookbook, which gives a lot of recommendations, but it's still a work in progress because as more people start to use the product, they'll discover different, more efficient ways to work around. At this point, I've not had a chance to do any of that. And if you find something really good, let me know, and maybe I'll write it up. One more question, and then we need to continue.
You probably mentioned earlier, but I missed it. What is the initial allocation size of the page?
There are no pages for the data. You mean for the index?
Yeah.
Index pages for your index pages, your leaf and your internal pages can be up to 8K, but they might, I think at this version, but any numeric question is subject to change. It might have been different in CTP1 and different in CTP2, and it might change again. I think, at least in CTP2, they're starting the actual index pages at 8K. The pages that are going to be a different size will be things like the special rows that are the delta rows. Those are officially considered index pages. The indicators that there is about to be a merge here is considered an index page, and those are the ones that are smaller, the ones that aren't the real index pages but the special information. Those are the ones that are smaller. That's subject to change as Microsoft itself looks for their own ways to optimize the whole product. Okay, so you need to keep in mind that all of the data for all of the memory optimized tables, the ones you've defined as in memory as part of the table definition, it's in memory at all times. So there is no paging in and out from disk. You need to make sure SQL Server has enough memory, and at this point there is an upper limit of 512 gigabytes for memory optimized objects. You can get errors at runtime. I have encountered errors at runtime just doing some of what I think are simple little demos, but I want to see what happens when a lot of rows go in. They're simple demos, but I'm putting in a lot of rows, and transactions can fail if we run out of memory, if I ran out of memory on my laptop here. And the memory management for your memory optimized tables is integrated with SQL Server's regular memory manager for the disk-based tables, and they do work in communication with each other if more space is needed for memory optimized tables, it may trigger the memory manager for the disk-based tables to free up some pages. They do communicate with each other. And also, as of CTP2, memory optimized, the whole in-memory OLTP system is integrated with Resource Governor, so you can bind a database to a resource pool, and that resource pool could have an upper limit of memory. If you don't want most of your memory to be eaten up by your memory optimized tables, you can bind the database to a resource group and set an upper limit there. But even if you want to use most of your memory for memory optimized tables, you can't. There is a hard physical limit of 80% of physical memory can be used for memory optimized tables across all your databases. So the rules of thumb for how much memory to plan for: you need to make sure you have space for all your rows, you need to make sure you have space for your indexes, and you need to make sure you have space for your versions before they're actually cleaned up. So a starting point might be twice your data size to make sure there's room for all the versions. You may find if it's a very volatile system that isn't enough. You might find that if it's not that volatile, that it's more than enough memory. For your index space, for hash indexes, you need, it's a fixed size on table startup, and we're going to see that in just a minute in a demo, that the size for your hash indexes is defined and allocated at table creation time. The range indexes are completely variable size depending upon how many rows, what the size of your key is, and how many modifications you're making, because we have to create new pages and keep a little bit of delta information that takes more space as we make changes in the range indexes. So we have some ability to do configuration. Our normal memory configuration will impact how much memory optimized space we can take up, and Resource Governor, I just mentioned, is also available for management. And monitoring, primarily we've got the DMVs, but what I'm just about to show you is there is a very nice report from the management studio that shows you how much memory you've used. Garbage collection is a regular ongoing process that SQL Server does to make sure that it doesn't take up more memory than necessary. As a row is deleted, it's considered stale. But if there are still transactions running that need to see that row, the row cannot be cleaned up until all transactions that started before the delete are finally finished. But there is a background thread that goes through and looks for stale rows, looks to see if anyone still needs them, and will start to mark them for collection, and then user processes as they go through looking for other data. If they find a stale row, user processes can actually remove rows from the index chains. We'll see that in a picture on the next slide, I believe. Here we've got an index page and a transaction that starts at time 210 that's going to go through and select all the data here. When this transaction goes through, it will only be able to see rows that were inserted before time 210 and have not been deleted as of time 210. So that means it will only be able to see the second row. The first row was deleted before transaction 4 started. I'll zoom in a little bit here. The second row, the first row was deleted at time 100, so a transaction that starts at 210 will not return that row. It will return the second row, which was inserted at 200 and has not yet been deleted. The third row was already deleted at time 100, and the fourth row was inserted after this transaction started. So maybe it's a really slow scan of this set of rows, and a row gets added while it's scanning. It gets here and says, I can't return that row because that's not really there. It was inserted after this transaction started. SQL Server also maintains a value internally. The developers at Microsoft call it a hint. I think of hints as something you add to your code, so I don't like that word either, but that I haven't got them to change. They still call it the oldest active hint. I just call it information about the oldest active transaction. At this point, the oldest active transaction in the system started at time 175. So as any scan goes through the table, if it sees a row that was deleted before time 175, it can just say, we don't need this. Nobody's going to need this anymore. And as it's scanning through, it can just remove that row. A user process will unlink rows from an index that is being scanned. We can't really get rid of that row until it's unlinked from all of the indexes that point to it, but the user processes are cooperative, and they do a bunch of the unlinking, so the main garbage collection thread doesn't have quite so much work to do. And the links are then readjusted. Some key points here. Individual processes scanning can remove rows. They don't always, but they might. And this offloads work from the garbage collection thread. If you have an index that nobody's ever using, it may be that the rows are never going to be unlinked from that index. The only time rows are unlinked is if somebody's scanning through a particular index. That's why we need the main garbage collection thread to go through, and the term that they're using is to sweep the dusty corners that aren't touched by any of your regular index access. This main garbage collection thread has to go through and make sure all rows that have been deleted are unlinked from all indexes. So let me just show you a little bit about what's available to you through memory management. I'm sorry, a short question. All right. You know, that is a work in progress. Most of the work actually is done by the user processes going through. And this background thread, I did hear a number of every minute, like the normal garbage collection for deleted rows or for your row versioning with snapshot isolation. The testing that I've done doesn't seem to indicate it's going through quite that often, but that was what I was told. But they're still working on it. So I am using, actually, I thought it said CTP2 here, but that my memory is not correct. If I actually look at the version, this is a version created on October 3rd, so yes, this is CTP2 here. I knew it was because I have created range indexes here. I'm going to create a brand new database. And then to make a database capable of storing memory-optimized tables, I need a file group with the property memory-optimized data, or with the property that it contains memory-optimized data. Now, I can't create a table yet because I've specified a file group, but no file. I have to add a file to the file group that contains memory-optimized data. And now I can use the database and create a table. The table will be a perfectly normal table except for the indexes. I'm creating 3 indexes. The first example, they'll all be hash indexes. I'll rerun this and create range indexes in a few minutes, but all 3 indexes are hash indexes, and for hash indexes, I have to give a bucket count. If you want to pull out your calculators and do some math, you can see if you could estimate how much space this table will take up with its indexes. There are 1 million buckets for the first index, 1 million for the third, and 128K for the second one. Each hash bucket takes 8K. So the total amount of memory space needed for 1 million plus 1 million plus 128K times 8K each pointer, 8 bytes each pointer is how much space? Well, if we create the table, we could have SQL Server tell us that value. When the table's created, even though there's no data in the table yet, If I right-click on the database name, right-click on the database name and look up reports, there is a report called Memory Usage by Memory Optimized Objects. And when I run that report, even though there's no data in this table yet, there is index space taken up because those hash buckets were all created. And that's all the pink area here is the index used, and it is 17 megabytes. If you did the math, you would have come up with a number pretty close to 17 megabytes. So that is the initial memory report before I put in any data into this table. And then when I load in 1,000,000 rows into the table, those numbers will change. So I can also, there's also metadata to show me those same values. I'll show you that in a minute, but I'm going to insert the 1,000,000 rows in a loop here. Insert, insert, insert 1,000,000 times. Verify the number of rows when I'm done. And that cannot be the time. Are we really almost done? I was sure I wasn't going to have enough information here for you. I always think that. And this usually doesn't take this long. There we go. I've got 1,000,000 rows. And let's see the memory report now. Report. Now there's still the same amount of space used for the memory, for the indexes. Still the same 17 megabytes for the indexes, but now the data uses a lot of space. Here, my data is using 68, 69 megabytes. My index size has not changed, even though I've inserted a lot of rows there. So I want to just briefly make sure you're aware of how durability is managed, because everything's in memory. What happens when the server crashes or is brought down for some reason? You can actually define a table to say, I don't care about durability. You can define a memory optimized table to be non-durable, to just use for intermediate purposes, and it will never, ever have any of its contents written to disk. But the durable ones are the ones that are written to disk in a set of files in your file stream file group that you created when you define the database. So the on-disk storage is actually maintained as a set of pairs of files. We'll see that in just a minute. Data files and delta files. The data files contain the rows that have been inserted in a particular time span from transaction X to transaction Y. All the rows inserted in that time frame are in a data file, and in that same time frame, all the deletes, the rows that have been deleted from that set of rows, is written to a delta file. SQL Server stores the row ID of the deleted rows. So here we have a pair of files. We call the two files together a checkpoint file pair because they're written to disk, just like in your disk-based tables, changes are written to disk at checkpoint time. But the checkpoint that writes your memory optimized data is a separate checkpoint than the checkpoint that writes your disk-based tables, but it's still a checkpoint. Checkpoint writes a set of file pairs. The data file has a bunch of rows. The rows have the timestamp that they were inserted. They have a row ID, which is the row number within that transaction, and they have the table that that row came from, and then the actual data in the row, of course. The delta file has the time that the deleted row was inserted. It has the row ID within that transaction, so it knows exactly which row from the data file has been deleted, but it also has the timestamp of the delete operation in case the delete failed. By comparing the data in the delta file to the transaction log, it knows whether it really was deleted, whether it was part of a committed transaction or not. So this next slide just steps through what happens during checkpoint. SQL Server reads the transaction log, and the transaction log contains deletes and inserts for memory optimized tables, as well as all your normal log records for disk-based tables. So in my log here, I have a delete from a Hekaton table, some logging for a disk-based table I'm not going to worry about, another delete from a Hekaton table, another delete from a Hekaton table, and an insert from a Hekaton table. This is a portion of the log. Checkpoint is reading through it. It will read that first delete of a row that took place, that was inserted at time 150. So it will write to a checkpoint file. The checkpoint thread has files that have different ranges of values. It has a range from 100 to 199, 200 to 299, 300 to 399, etc. So reading through the log, the first delete will add a marker into the delta file for this first range because it was a row that was inserted at time 150. So that's the data file that delete has to be associated with. We ignore the disk-based operation. The delete from a row that was inserted at time 150 goes to the time 450, goes to the delta file for the range 400 to 499, and then the delete from 250 would be put into this this delta file here, and then a new insert will happen. So let's see that. The third delete will be written to, and that's the second delete. Oh, not going to the right place. I'm sorry, I'm going to have to check my animation here. But the insert is a current insert, or is an insert that happened at this timestamp, and it goes into the last range there. So we've got this set of rows that have been inserted, but then rows that have been deleted from that set written out every time a checkpoint occurs. If there's a failure, these files can be used to recreate all your data. I have a slide on that recovery process that we're obviously not going to have time for. I will, let's see, I want to make sure I cover some of the most important things to be aware of here. We have another use of the word merge. We merge pages in the BW tree index as rows are deleted, but we also merge some of these files as the number of deletes gets too big. We don't want to keep around all these rows when a big percentage of them has been deleted, so we can merge adjacent files together. This not only saves disk space, but it also means that the recovery process can be a lot faster. There is a metadata view. Here's our first look at the name of a metadata view, DMXTP checkpoint files. There's that XTP for extreme transaction processing. And it basically, the two purposes, save disk space and improve the recovery time. This is an online and background operation. You may never know it's happening if you're not keeping an eye on the metadata. So there's an animation to step through the merge process. I don't think I'm going to do that. What I do want to show you is one more demo, because there's something really cool in this demo that I want to make sure I get to. And I know I'm a little past time, so if you need to leave for another engagement, I won't be too insulted. Like lunch, I know. It's like lunchtime. A brand new database this time called Storage Demo. I'm going to create the database with a file group that contains memory. Oh, no, that's the, yeah, this is the file group that contains memory optimized data. And then I'm going to add a file group, a file to that file group. No, that wasn't yet. Maybe this is not the demo I was thinking of. No, I'm just going to use that file, use that database, and create a table. Actually, before I create the table, I wanted to go out to disk and show you where I've created this. This is for Storage Demo. Storage Demo has a container, and then within that container, If you've worked with file stream, the files look just like the file stream data, a bunch of funny named files, and you can see some of them are pre-allocated and some of them are not. Some of them are 128K, which is the basic unit of writing to disk. It's not the maximum size that one of these files can be, but it's the initial size when space is first allocated. Some are not populated yet. These are the delta files. These are the data files. And as we start making changes, we'll be able to see these files. We'll either see more files or we'll see these files growing. You can look in that location and see storage space changes. So I'm going to create a table with a range index this time. And I'm sorry I did not get to show you the other demo with range indexes, but but you can do the same thing. You can create a range index and just look at the memory space and see that there's no space when you first create the table, only space after you start inserting rows. I'm going to insert, I've created two tables here. I've created a disk-based table and a memory-optimized table, and I'm going to insert 100 rows into each of them. I'm going to insert 100 rows into the disk-based table. That shouldn't take too long. And then you might be aware of a function that allows you to read the transaction log. What the purpose of this demo is to show you how much less logging takes place for changes to memory optimized tables. One thing that saves logging is you don't log anything about changes to the index because those are never recovered, those are never redone. They are only to maintain the rows in memory. So I can look in the log, and there are 200 rows for this particular, oh, it doesn't say there. There are 200 rows for this particular object because there's an insert into the row itself and an insert into the index, and each row is a fixed length size, and I can add up all of that size information and see that for that one insert of 100 rows, it took 32K of log space. Or if I do a very similar thing to my memory optimized table, did I not create that table? That makes rushing through demos not a really nice thing. Let's create that memory optimized table. I'm in a transaction still? I'm so sorry. I am not in a transaction still. All right. I got that error once before, that it said I was in a transaction when I wasn't.
You didn't create the physical file for the...
Yes, I did. I did, and because now this time it succeeded. I had this error before. And that's the same thing. Someone said, make sure you've created the file, and I had, and I just ran it a second time, and I didn't get the same error. So I've got a Hekaton table now, and I'm going to insert 100 rows into it. And look at the log now, and all I have, if I look at the very top of the log, there's a whole bunch more rows in it now in the log, but the whole Hekaton transaction is just those 3 log records. Begin the transaction, do something with Hekaton data. It still uses the HK there for Hekaton, and the whole thing, yeah, it was a little bit bigger than the log records for the disk-based tables, but not 35 kilobytes. It was definitely just a fraction. It's about a third of the space. But there is another function that allows us to look inside a Hekaton log record. If we pull out the transaction ID and pass it as a value into this function called fin dblog xtp, it will show me all the changes to the Hekaton table, and there are 102 rows here. The begin transaction, the 100 rows inserted, and the commit transaction. So we've got the ability to actually break apart our log records and see what was actually done into our memory optimized tables. Now, a few comments about the logging, but the main thing is the log records are all combined in SQL Server's own transaction log. All the operations for a single transaction are combined into one Hekaton log record. All logging is logical. No physical page representations, only the rows that were impacted during your operations. All 3 recovery models are supported. How much disk space do you need? You need to make sure you have space for the files, and if the files have not yet been merged and lots of rows have been deleted, you might need even more space. And I know I'm out of time here. Lunch is starting, and they want you to go to lunch, so I'm not going to be able to finish. But I appreciate your attention for what I was able to cover. My white paper, the best place to get it is through my blog. On sqlblog.com, I have a link talking about the release of the CTP2 white paper, and that's probably the quickest way to find how to get that paper. And there's a whole bunch of information, everything I've talked about today, and more besides. All the scripts are pretty much in that white paper also. So thank you very much, and I apologize for the rush. Thank you.